So let's take a look at the limit comparison test. So remember that usually when the direct comparison test does not work, you will use the limit comparison test instead. So the formula for the limit comparison, let's say you are given the series of a sub n. Similar to the direct comparison test, we're just going to find a very similar series, b sub n. Now if b sub n converges, or if the series b sub n converges, and you take the limit as n approaches infinity of a sub n over b sub n, and you get some finite value c, where c is greater than 0, and remember it has to be a finite value, then a sub n, both a sub n and b sub n converge as well. Now let's say b sub n, the series of b sub n diverges, and you take the limit of a sub n over b sub n and you get c, where c is greater than 0, then it will also, both a sub n and b sub n, both series will also diverge as well. So looking at number 1, we have the series from 1 to infinity of 1 over the square root of n squared plus 1. So in order to compare this and use the limit comparison test, we have to compare this to a similar series. So notice how the highest degree on the numerator is 1 and the highest degree on the denominator is n squared. And the square root of n squared is just n. So I can really compare this to 1 over n. And we know 1 over n is the divergent harmonic series. So, or we can use the p-test. So p equals 1, 1 is equal to 1, which means that the series will diverge because of the p-test or because it's a divergent harmonic series. Now what we can do is take the limit. The limit as n approaches infinity of the a sub n over b sub n. So it doesn't matter which one you put on top of the other, you can put any one. So I'll just go ahead and put 1 over the square root of n squared plus 1 and divide it by 1 over n. Dividing by 1 over n is the same thing as multiplying by n, the reciprocal. So the limit as n approaches infinity, we get n over the square root of n squared plus 1. Now when we're looking at n behavior, we're just looking at the most significant terms, or the highest degree. So the highest degree on the numerator is n, and the highest degree on the denominator is the square root of n squared. So if the limit as n approaches infinity of n over the square root of n squared is just n, and so that is equal to 1. So remember, the limit has to be positive and the limit has to be greater than 0. So it is positive and it is greater than 0. And so if the similar series that we compared it to diverged and the limit we get is greater than 0 and is a finite number, this means that the series of 1 over the square root of n squared plus 1 also diverges, but this time by the limit comparison test. So notice how the limit comparison and direct comparison have the same first couple steps, where we find a similar series and sort of find whether that series will converge or diverge. Now for number 2, we have the series from 1 to infinity of sine of 1 over n. Now this is a little bit tricky at first, but it will help if you can graph it on your calculator. So if you look at the graph of sine of 1 over x, it's going to look something like this from 1 to infinity. Notice how this is sort of close to the graph of 1 over x, or sort of looks like it in some parts, which tells me that I don't even have to worry about the sign. I can compare this to the graph of 1 over n. So I compare this to the series of 1 over n, and obviously 1 over n is a divergent harmonic series, so we can say it diverges by the p-test or divergent harmonic series. And now we can set up a limit. So the limit as n approaches infinity. Remember, I can put either one on top of the other. So I'll just put sine of 1 over n on top, and then divided by the other series 1 over n. So notice if I plug in infinity, 1 over infinity is 0 and sine of 0 is 0, and 1 over infinity is obviously 0. So when we get 0 over 0 or an indeterminate form, we can use L'Hopital's. So we just take the derivative of the top and the bottom. So first I'm going to change 1 over n to be n to the negative first power, just so it's a little bit easier to use the power rule. So sine of n to the negative first over n to the negative first. Now remember, the derivative of sine of u is going to be equal to cosine of u times u prime. So the derivative of sine of n to the negative first is going to be cosine of n to the negative first times the derivative of the inside function. And the derivative of n to the negative first, we can just use the power rule, where we bring the power down and subtract the power by 1. So we have negative 1 times n to the negative second power, divided by the derivative of the bottom, the derivative of n to the negative first. We just did that with sine of n to the negative first. It's going to be negative 1 n to the negative second. So notice how these two terms will cancel, and we'll be left with the limit as n approaches infinity of cosine of n to the negative first, or cosine of 1 over n. When I plug in infinity, we'll get cosine of 1 over infinity. 1 over infinity is 0, and cosine of 0 is going to be equal to the value of 1. Our limit is a finite number and is greater than 0. So if our comparison series diverged, then, or this series, sine of 1 over n, will also diverge. By the limit comparison test.